Imagine throwing a ball up into the air. The harder you throw it, the faster it travels, and the higher it goes before falling back down. If you threw it hard enough, it would actually fly away from the Earth like a rocket. But what if the Earth was condensed to the volume of a marble? No matter how hard you threw your ball, it would always fall back down to you. It could never escape. This marble-sized Earth has essentially become a black hole, a region of space with a gravitational field so strong that nothing, not even light, can escape. Let's go back to when the Earth was at its normal volume. The speed that an object must be traveling at when it leaves the surface of the Earth is called the Earth's escape velocity. The escape velocity of the Earth depends on the gravitational pull that the Earth exerts on the object that's trying to escape. Gravity is an attractive force between objects with mass. The gravitational force between two objects depends on their mass and the distance between their centers. The greater their masses and the shorter the distance between each object, the greater gravitational pull one exerts on the other, and therefore the higher the escape velocity must be. Since the mass of the Earth is many times larger than the objects we launch from it, the mass of the object is considered insignificant, and scientists only consider the Earth's mass when determining how fast an object, like a rocket or your ball, has to go to escape the Earth. In such an estimation, the Earth's escape velocity is about 39,000 kilometers per hour. Roughly 50 times faster than the average speed of an airplane. Now let's revisit our marble-sized Earth. In this scenario, the Earth is smaller in diameter but unchanged in mass. The escape velocity will be higher since an object on the Earth's surface would be much closer to its center. If we were to continue squishing the Earth, the escape velocity would approach the speed of light. Nothing can move faster than the speed of light, so your ball, or any object for that matter, could never achieve a high enough velocity to escape the compressed Earth. This is how the Earth would become a black hole. 100 years ago, the existence of black holes was speculation. Scientists had developed numerous theories that used black holes as tools for understanding the fundamental laws of the universe, like explaining the beginning of time. In this way, scientists had mathematical proof that black holes must exist, but little physical evidence to support the theory. After all, how can you see something from which no light escapes? Astrophysicists theorized that they could instead try to capture the silhouette of a black hole. Since black holes exert an extremely strong gravitational pull, any nearby matter is rapidly drawn towards them, creating an accretion disk that spirals inward. The accretion disk exists just outside of a black hole's event horizon, which can be thought of as the point of no return. Anything that passes the event horizon will be sucked in by the intense gravity of the black hole. Due to frictional heating, the fast-moving matter in the accretion disk glows, emitting light. This light is bent by the gravity of the black hole, creating a glowing ring that we can see. In 2019, scientists did just that. They observed a ring of light emanating from an accretion disk. This visually confirmed the existence of black holes for the first time in history. Using an array of 8 ground-based telescopes across our planet, astrophysicists captured images of a massive black hole at the center of Messier 87, a galaxy 55 million light-years from Earth. This major breakthrough served to support decades-old scientific theories about black holes, and even some of the stories that science fiction authors had written about them. With increasingly complex technology that allows us to observe the depths of our universe at higher resolution, scientists increase our understanding of cosmic phenomena and find new questions to ask, ranging from the potential to harvest energy from a black hole, to discovering plasma jets, streams of energy and hot matter that spew from the center of black holes. With a gravitational force so immense, it's no wonder that scientists can't escape the irresistible mysteries hidden deep within black holes.